All right, so Ohm's law. It's probably one of the simplest relations you'll ever see. Ohm's law. All right, so it's extremely simple. And what we see is V is equal to IR. V is equal to IR. All right, you can probably guess what a lot of this is serving to represent. This guy is the voltage. V represents voltage, right? We talked about that before. We are also talked about that this represents current. So this is what's flowing in the circuit. And then R, you might guess, is resistance. So that's it, ladies and gentlemen. It is probably the simplest algebraic equation you can come up with. V is equal to IR. The voltage in a circuit, right, is equal to exactly the current flowing through some device in the circuit times the resistance of that object. So when you think of Ohm's law, you really should think about it in terms of it being applied to any specific element in a circuit. So envision a circuit, you've got a source that's some battery or something pushing electricity out, and then there's some other stuff. The other stuff could be lots and lots of things. Could be a fan, could be a light bulb, whatever. But in our study of circuits, we're going to begin by talking about resistors, resistive networks. So think about some resistors over there. So the current is going to be going through those resistances. So whatever the current is that's flowing through a resistor, multiplied times the resistance value itself in ohms, is going to tell you what the voltage drop, what the voltage is across that resistor, right? So I think let's talk about it in a little more detail, and you'll see it with some pictures as well. Now, before we get to that point, most books will introduce Ohm's law being V is equal to IR. Now, it's a simple algebra equation. You can solve for I, if you wanted to calculate the current, you could just divide both sides by R. I would be equal to V over R. So a lot of times in books, this is honestly the way I like to remember it myself, I is equal to V over R. It's exactly the same relation. It's not like this is a separate equation from this. It's all the same thing. This is the relation. When you solve for current, it means you divide by the resistance like this. If you want to solve for the resistance, you just divide by the current, so it'd be V over I. All right, but this particular form is nice to talk about verbally because you can see very easily a few nice things about Ohm's law. Think about it. What we're saying is, if you have an object in your circuit, firstly, you got to remember, Ohm's law applies to everything in the circuit, all the resistors. Later on, it'll be a slightly different story, but basically it's going to apply to capacitors and inductors and everything else going on. At any point in the circuit, if you get a meter out and you put the little probes onto the circuit and measure the voltage across some object, right? Then this voltage divided by the resistance of the object, the resistor in this case, is going to tell you how many amps of current is flowing through that resistor. And this relation, whatever one you want to look at, it applies to every single object, every single resistor, and everything else in the circuit. It applies everywhere, all right? So it's universally true. But when we look at it written in this form, we can see a few nice things. If the current through an object in a circuit like a resistor truly is equal to V over R, then if we increase the voltage, just forget about numbers, if we just increase the voltage, then this numerator gets bigger, then that means the current must get larger, right? If we increase the voltage. Think about what the voltage is. It's the push. If I increase the voltage, if I turn a knob up and increase the voltage, I'm pushing more, so to speak, on the electrons. What this is saying is I'm going to get more current because this numerator gets bigger. And that's exactly what we said in section 1. Now, what if I do the opposite? What if I hold everything else constant and I increase the resistance? Right? What's going to happen? If I have a circuit with a resistor in there and I slowly increase the value of that resistance and hold everything else constant, this denominator is going to get larger and larger and larger, and it's going to drive the current down because this gets bigger. So that means the current goes down. So if I increase the resistance, we talked about in section 1, if I make more resistance, my current is going to go down. Right? If I increase the voltage, I'm pushing more, my current goes up. So I guess what I'm trying to say is you can see from the math that Ohm's law, as we've written it, is everything that we talked about in section 1. It's just mathematically saying the same thing. You push more, you get more current. You increase the resistance, you get less current. It's basically all it says. So it gets a little bit trickier when you're applying it to complicated circuits, but that's basically it. Now, what we want to do is apply this knowledge here to a real circuit. And again, I told you these are going to be simple circuits because, believe me, you need to be able to crawl before you walk. So here we have a source, and let's say this is a 10-volt source. And we're going to have a very simple circuit like this. It's just one loop. That's all it is. This resistor over here is known to be 5 ohms. 5 ohms. This is 10 volts. All right. Now, once we hook this thing up, there is going to be a current that goes this way. Remember, current always comes out of the positive terminal and goes around and around and around and around and around and around like this. It just keeps going on and on and on until the battery dies. Or if it's plugged into some kind of power supply, then it'll just stay going on forever, right? The question is, what is the value of this current? What is the value of this current? So the way you should think about this, there's a lot of different ways to think about it, but basically you need to look at Ohm's law here, right? The current is equal to the voltage divided by the resistance. So you need to apply Ohm's law to something in the circuit. So we're going to apply it to this resistor. Now, this is where I need to really spend some time making sure you understand. Because you have this voltage source connected by a wire, and by the way, when we use wires in circuit diagrams, we presume that those wires are perfect. They don't have any resistance, they're not really any, they're just absolutely perfect wires that carry electricity perfectly. So the only resistance in this entire circuit is this. It's not in the wire, it's not in anywhere else, it's only in this. That's because it's a perfect circuit. Now in real life, the wire really does have a tiny bit of resistance. So we have 5 ohms here. Because we have connected this battery up directly to the terminals of this resistor, then this voltage that's here, plus minus, is also present across the resistor. Is also present across the resistor. Where the positive is side of the voltage is here and negative here. So it's just the same sign convention of what you had before. All right, so let's go through the problem and I'll come back to explaining it. So what is this voltage drop across the resistor? Well, it's the same voltage that we have in our source because it's physically connected to the resistor. So if we got a meter out and touched the edge of each side of this resistor, the meter would read 10 volts because that's what's physically connected to the source, right? If we put the voltage leads here, it would measure 10 volts. If we put them here, it would measure 10 volts. If we put them here, it would measure 10 volts because it's all connected to the same place. So we know that the voltage drop across that resistor is 10 volts. We know this to be true because 10 volts is connected here. So what we do is then we say the current in this circuit, or the current through the resistor, which the current here, I've drawn it here, is the same value of the current all the way around. It's the same value of the current because it's one circle. So the current going through this resistor, which is the same as this current in this part here, is equal to the voltage across that resistor divided by the resistance itself. The voltage across the resistor is 10 volts because it's exactly equal to the source since it's physically connected there. And the resistance is 5 ohms. So when you're doing these calculations, you always want to deal with volts and ohms. Those are the base units we talked about. So I is going to be 10 divided by 5, which is 2, and the unit of current is amperes or amps. So there we go, you circle that. So what this is saying is that in this circuit there are 2 amps of current flowing through this resistor, and of course since it's simply one loop, there's 2 amps of current going all the way around and around and around and around all the time. So, you know, very, very important that you understand that. The other thing to make sure you realize and just know as we study all these circuits is that every component that you have, we call this a passive component. Passive because there's no power supply going on. It's just kind of receiving the current. This would be an active component. It's supplying electricity to everything else, or it's called a source really. But everything else in the circuit where the current's just flowing is called a passive component. These passive components, once you energize the circuit or you let the current start flowing, if you put a wire, you know, the circuit meter, you've got a multimeter from the store, and put it across that resistance, you're going to see a voltage drop because there has to be a mechanism to push the current through this guy. Obviously it's coming from the source, but there's going to be a voltage drop across every single resistor in your circuit, and that voltage drop is going to be governed by Ohm's law because we know there's a current going through it, we know there's a resistance here, so there has to be a voltage across that resistor and across every resistor in a circuit. That's what Ohm's law tells you. All right? So, I just want to make sure you understand that because it's so very important. Now let's go and do another one here. Again, they're going to be all pretty simple. Let's go and do another one, and then we'll come back and talk a little bit more. Let's say we had slightly different numbers. Let's again keep this constant at 10 volts. It's going to be a single loop circuit like this, and this is going to be now 10 ohms. All right, now obviously there's still going to be current going through here like that. And it's the same current in every little part of the circuit because it's one loop, right? So what we know is we have 10 volts, same as before, but we've increased the resistance. So we expect, since we've increased the resistance, we expect there to be less current, right? So what we need to do is figure out, using Ohm's law, what that is. I, the current, is going to be equal to V over R, right? So you have to apply it to something in the circuit. Let's apply it to this resistor. The current through this resistor is going to equal the voltage drop across this resistor divided by its resistance. What is the voltage drop here? Well, it's not labeled in your diagram, but since you've connected this source directly to the terminals, the voltage drop across, if you were to measure it with a meter, would be 10 volts divided by its resistance of 10 ohms. So when you do all of this, the current is equal to 1 ampere, 1 amp. So if you were to measure, you would put a meter in there and measure how much current's actually running around the circuit. Notice that the current now is half as much as the current was in the first case. The reason it's half as much current is because we have exactly doubled the resistance. It's because Ohm's law is a simple algebra equation. If you double the resistance, you're going to halve the current. I mean, there's no squares anywhere, there's no square roots, it's not really complicated, but you do need to understand what you're doing. Now, since I have two problems on the board, even though they're basically the same circuit, I want to make sure you understand and start to visualize as you look at circuits. You know, this is so simple, you know the current is going here. But anytime you see current going through a resistor, there's going to be a voltage drop, positive to negative, across that resistor in the direction of the current flow. Because you need to think of it as almost like the voltage here, right, that's across the resistor is what pushes the current through this resistance, for lack of a better word. And the way we do the sign convention in engineering is that whenever you're talking about a passive component like a resistor or almost anything else, a capacitor or inductor, everything we're going to talk about is called passive component, then the voltage drop is going to, we call it a voltage drop for a reason, because it goes in the direction positive to negative of the current flow, positive to negative, right? When the current comes back around, if you notice the current goes this way, it goes from negative up to positive. That's totally opposite of what it's doing here, but that's because these are special. This is a source. It basically boils down to sources are generating, they're basically supplying the power to the circuit. So anytime you see current going from negative to positive, it's kind of unnatural. It has to be a source supplying that from some external supply of energy, right? But everything else in the circuit, you're going to see a drop in voltage from positive to negative. Now I want to take a little bit of an aside and tell you sort of like an analogy here to make sure you understand what I'm talking about here. Voltage is kind of like potential energy from physics, right? Potential energy. If I go up to the top of a mountain, I have more potential energy, more potential to do work, right? Because I'm higher off the ground, right? That's what we would sort of think about as a high voltage up there, right? High voltage means more potential to do something, more potential to push electricity, right? If I take a bowling ball and roll it down the mountain, right, a certain distance, and then you stop it halfway down the mountain, right? And then you look and see where you are halfway down the mountain, you have less potential energy. You have lost a little bit of potential energy because you started at the top of the mountain and you used some of that energy to get halfway down because the ball rolled down, right? And you stop again before you hit the ground, so you're halfway up this mountain. You still have some potential energy, but not quite as much as you had to begin with. You've lost, you could sort of say you've dropped your potential energy. You went through a potential energy drop, right? That's all we're saying here. This source is supplying 10 volts. It's like giving a lot of potential energy to this resistor, and that potential energy is pushing this current, and as the current goes through the resistor, it's kind of like once it makes its way through this resistance, it's dropped its potential energy as it comes around to the other side. So I guess I'm trying to explain the sign convention in ways that you can kind of understand. That's why it's positive up here and negative. Don't get too wrapped up in the signs here. It just means that this side of the resistor had a higher potential energy, for instance. Once it forced the current down to the bottom of the mountain, then over here we had less potential energy than we started with. with. Now, if we had like 5 resistors in a row, like one wired up after another, each one of those resistors would take away a little bit of potential energy from the source. And by the time we got down to the bottom, we'd be back to the bottom of the mountain again, so to speak. So think of your batteries or your wall sockets as supplying energy to the circuit, almost like the top of a mountain. As you walk around the circuit, you're losing voltage, so to speak. So you're doing a voltage drop from here to here as you cross this resistor and as you get back around to the source. Now I'm going to have a few more examples to kind of illustrate this a little bit more, but I wanted to make sure you kind of understand that. Bottom line, if you don't want to remember anything else, if current is flowing through a resistor, you're going to have a voltage drop, positive to negative, always, always, always. That's the voltage we're using in Ohm's law. All right? So let's go and do another one. It's going to be the same thing. I'm just going to change the numbers again because I want to give you a lot of experience. So if it's 10 volts again, all right, and make it 20 ohms. Okay, 20 ohms. And again, I want to know what I is here. Now notice I'm drawing the current I in different places all over the place. I'm trying to kind of drill that in, that the current is the same everywhere. So what we need to do to find this current is I is equal to V over R. Of course, that's exactly the same thing as V is equal to IR. You could use this guy, or basically rearranging the equation either way. It's the same thing. So if we want to calculate this current, we need to know the voltage across this resistor. What is the voltage across that resistor? Well, it's physically connected to the entire voltage source, so the voltage drop across this resistor is 10 volts, and this resistance is 20 ohms. So we do this division, it's 1/2, which is 0.5, and the unit of current is always amperes, 0.5 amps, half an amp. All right, so I guess I wanted to show you the progression. If you have the same source in all the cases, you start with 5 ohms, you have 2 amps of current. Increase the resistance by doubling it to 10 ohms, you drop your current to 1 amp. All right, if you increase your resistance again to 20 ohms, you get even less current. Now we're at half an amp. All right, so that kind of just illustrates what we talked about in section 1. If you keep jacking up the resistance, your current's going to go down, down, down. All right. Now let's do a little different. The circuit will look the same, but the numbers will be a little bit different. Let's change this to 1 volts. This is now a 1 volt source. And now instead of a resistance that we've been talking about before, this will be 50 ohms. 50 ohms. So this is quite different. See, what we've done now is we've decreased the voltage, which means we've decreased the push, right? And at the same time, we've also increased the resistance. So both of those things combined together should dramatically decrease our current, because now we have less of a push and we have more resistance in the way, more resistance getting in our way. So again, V is equal to IR. We can use this version if we want. The voltage, we have to talk about something. Let's talk about this resistor here. Notice that the current is going to come this way because it's going round and round. Anytime we go through a resistor, there's going to be a voltage drop. This voltage drop is the same as the source because it's connected like this. That voltage is 1 volt. So we have to talk about a component when we apply Ohm's law like this. Is equal to I, we don't know what I is, but the resistance we know is 50 ohms. So we have volts and ohms, so the units are fine. So the current is 1 divided by 50. So the current, 1 divided by 50 is 0.02 amps. Now it's perfectly fine. Notice that we have a very, very tiny current now because we've decreased our voltage, our source, and at the same time we've increased our resistance quite a bit. So both of those things together drive our current down, just like we talked about. Now notice that we have a very small current, much less than 1 amp. So now it might make sense to rewrite this in terms of milliamps, and that's exactly why I'm presenting this to you here. If you think about it for a second, this is going to be equal to 20 milliamps, because milli means you shift the decimal point 3 places. So if you take 20, it's the same thing as like 20 times 10 to the minus 3 because of milliohms, milliamps is 10 to the minus 3. So if your decimal is here and you move it 3 places to the left, it'll be 1, 2, 3, and you get your 0 there, which is exactly here. Another way to think of it is if you're going to go from here to milliamps, you need to shift the decimal 3 places, 1, 2, 3. So it's going to be 20 milliamps. If you get confused on how to go quickly from milliamps back to amps, or kilo ohms back to ohms, or if that metric conversion is tough for you, go get the unit conversion tutor, because the unit conversion tutor that I have just gives you lots of examples with dealing with the metric system. But this is just moving the decimal point by 3 spots. All right. Let's say you have a problem where your source is not a nice number of volts that you might think about. Maybe it's, instead of 50 volts, maybe it's 50 millivolts. The MV means millivolts. 1/1000th of a volt, in other words. And let's say, again, that's connected to just a single resistor. This resistor, let's say, we don't even know what it is. It's just resistance R. We don't even know what it is. And let's say that the current flowing through this circuit is denoted by I, and that's 10 milliamps, right? So here I'm giving you a problem where we know the voltage and the voltage, right? We know the current, but instead of volts and amps, we're giving millivolts and milliamps, right? So what you need to be careful about is whenever you use Ohm's law, you always have to use volts and amps. I guess once you get some experience, you can start mixing units and you kind of know what should come out the other end. But in the beginning, I always recommend for you to just convert everything to volts and amps. And the easiest way to do that is, if we want to know what this resistance here, just use Ohm's law. V is equal to IR. We have to apply it to this resistor. Now we know that there's going to be a voltage drop through this resistor because the current is coming this direction. You always need to get in the habit of seeing that. When you see the current going through something, plus minus, you should just think of that. If you put a meter here, that's what you would measure. This voltage drop is what's pushing the current through. Of course, that voltage drop is also coming from the source. That's the original genesis of the whole thing. But whenever you use this guy, the voltage here is 50 millivolts. Now, you don't want to put 50 in here. You want to put 50 times 10 to the minus 3, because that's what millivolts is. You take the number and you multiply by 10 to the minus 3. Equals, the current is 10 milliamps. You don't want to put 10, you want to put 10 times 10 to the minus 3. And this will give you all the credit on your exams too if you make a calculational mistake, times R. So it's the same thing. The voltage across the resistor, the current through the resistor, the value of the resistor is unknown. Now if you grab your calculator and you take 50 times 10 to the minus 3 and you divide it by 10 times 10 to the minus 3, just moving this over here, basically giving you the resistance is going to basically be equal to 5 ohms. And that's what's going to spit out there, 5 ohms. So make sure, I guess what I'm trying to do by showing you this problem is make sure that when you're presented with milliamps or microamps or kilo ohms or whatever, when you're doing your calculations in Ohm's law, don't forget that you need to always work with volts, ohms, and amps, all right? So you need to work with those base units. If you accidentally put millivolts in here and then put, instead of milliamps, maybe you accidentally put 10 here instead of 10 times 10 to the minus 3, and you mixed it with something different over here that didn't match, then you're going to get into trouble. So what we've done is implicitly converted back to volts and amps and so on to be able to do the calculation. All right, so far we've done single loop, right, with a single resistor. And the most important thing I wanted to drill into is how to use Ohm's law, how to deal with the units, right, and also to visualize those voltage drops that go across those components when the current flows through them, because it's so important. We're going to be doing methods later on when we do analysis where you're going to have to use that knowledge over and over and over again. So I'm really trying to drill it into you. Now what I want to do is erase the board and show you a couple of circuits with more than one resistor. Not going to be too complicated, but it'll allow us to visualize a few things that the simpler circuits, we need to be able to build beyond that. So we're going to do that right now. All right, now our next circuit is going to be quite a bit different from what we've talked about before, but it illustrates something very, very important. So let's say we have 12 volt source, and this source is connected to a resistor here and also another resistor in series with it. We call this in series when something is just one after another like that. All right, now this resistor here, we know, because we bought these resistors, that this is a 1 ohm resistor, and this resistor is a 2 ohm resistor. So we have 1 ohm in series with 2 ohms. And we also know, just because we happen to measure, let's say, that the current going through the circuit is 4 amps. Now don't forget what this means. This means that 4 amps is going all the way around through both of these resistors back up to the source and around again. If we had a branch here, if we had another part of the circuit that came off like this, then this current would end up splitting here, and then coming back and rejoining here and going back to the source. So anytime you see circuits with lots of branches, right, you can envision that current splitting off and then circulating around and coming back together, much like a water hose might do in a sprinkler system. Water split off, go back and do its thing, come back together and go back, if you had a circuit going, a circulation pump, it'd be coming back to the pump, right? Same thing here. But this is much simpler because we only have basically one branch there. It's just that in this branch we have two resistances there. So, question number 1, right? And let's just call this, just to make it easier to understand, let's call this R1 and R2, resistance 1 and resistance 2. Now, let's say, what is resistance 1? What is resistance 1, right? Specifically, what is the voltage across resistance 1? So we might have something like this drawn on our paper. We might have little holes like this, plus minus V1. You might see this drawn like something like this. All this means is here is the circuit, right? Electricity is going like this. We stick a probe in and we measure the voltage only across resistance 1. What is that voltage, right? And we call it V1 because it matches up with R1. How do we calculate that voltage? Well, anytime you have to calculate voltage, you're always going to use Ohm's law, right? So we need to use V is equal to IR. And we're going to apply it to this resistance because that's the one we care about. That's the one that this problem's dealing with. So what is the voltage across this guy? We call it V1, let's say. We don't know what it is, so we just leave it there. Equals. What is the current flowing through this resistor? The current here is 4 amps. It's the same 4 amps that keeps going around over and over again. So we call it 4. Right? The resistance is known to be 1 ohm. So we just put a 1 here. So V1 is equal to 1 times 4, which is 4 volts, right? So in other words, this is 4 volts right there, right? Is equal to V1. So if you put a probe there, a voltmeter, and you measure it, you're going to see 4 volts across V1. Notice when we applied Ohm's law, we didn't even care about what R2 was doing. It didn't matter. If we know what the resistance of this R1 is, and we know what the current is going through that resistance, all we need to know is what the value of the resistor is and what the current is going through it to calculate the voltage. What voltage are we talking about? It's the voltage across the element that we're talking about. So you see, a lot of times before you take circuit theory, people toss around voltage and current like they're just these broad terms, right? But when you're analyzing a circuit, when you talk about a voltage, you're not just talking about a voltage here or here. You're always talking about the voltage drop across some circuit element. That's what you mean when you say voltage. When we say this is a 12-volt battery, we're saying that this is a voltage difference between the terminals of these two the ends of the battery, let's say. Or if it's a wall socket, it's the voltage across the two ends. That's how you develop that push. It's always between 2 points. So when we talk about the voltage here, right, it's labeled across R1. That's the voltage drop coming from, if we had to, well, we actually put plus minus here. High, dropping down just a little bit as we drop across, kind of coming down the mountain, so to speak. Now you might guess, the next thing I want to ask is what is the voltage drop across R2, right? So it would be V2 is equal to IR2, right? So the voltage drop across this guy is going to be equal to I times R2. So if we were going to, just to make sure it's absolutely clear, 12 volts, resistor here, this is R1, which we already labeled as 1 ohm. This is 2 ohms. And we know the current is 4 amps that's going through the circuit. If we're talking about this guy, you might see it drawn in a book like this. The little circles here indicate that it's not really part of the circuit, it's just that you're measuring the voltage across this element, right? And it's going to be plus minus because the current is going and dropping across through that resistor, so we always have a voltage drop like that across these passive elements. V2, which is what this is, voltage across resistor 2, is equal to the current times R2. V equals IR. So, V2 is equal to the current flowing through this element is the only thing we care about, and that current is 4 amps because it's the same guys that's flowing around everywhere else, times 2 because we have the resistance of 2 ohms here. So V2, the voltage across resistor 2, is 8 volts, right? So what you'd have if you actually measured this guy is you'd have 8 volts across this element. All right, so what I really wanted to do by illustrating this, there's lots of ways to analyze a circuit. I could have done lots of things. I could have showed you how to add these resistors together and do something slightly different. What I'm trying to show you is that the only thing that matters is the current flowing through that particular resistor and the value of that resistance in order to calculate the voltage. Or likewise, if another circuit gave you the value of this voltage drop across this resistor, and you know the value of the resistance, then you have enough information to calculate the current. All you care about with V is equal to IR is the voltage across the element, the current through the element, and the resistance of the element. And that's what it applies to. So when you apply Ohm's law around your circuit, you just need to be able to zero in on whatever it is you're talking about. Now, before we close the section, I want to sum this up because there's actually a nice lesson in here that I really want you to be aware of. So let me change colors a little bit just to make it pop off the board. I'm going to redraw the circuit one last time. This will be the last time, 12 volts. So we had a resistor here, and we had a resistor in series, like this. And basically, I'm not going to label everything again, but I am going to put that this is 1 ohm and that this is 2 ohm, and that this is 4 amps. That was flowing through the circuit. And basically what we figured out is that if we put a probe across this resistor, like this, what we figured out that the voltage drop would be up here, 4 volts. So this is 4 volts here, all right? And we also figured out that if we measure the voltage drop across the second one, so we can have this like a common little terminal here, and then the voltage drop from here to here would be, again, plus minus, and the value would be 8 volts. So literally, if you went and got a 12-volt battery from the store and hooked a 1 ohm resistor in series with a 2 ohm resistor, and then you got a voltmeter and you measured across here, you would measure 4 volts. And if you got a voltmeter and measured across here, you would see 8 volts in accordance with our calculations. But what do you notice? 4 plus 8 is equal to what? 12. 12 is the total voltage that we started with. This is a very important lesson that I'm really trying to point out to you here, that a lot of times you don't really see it until you work enough circuit problems. What we have here is a situation where, you see, remember back to the other problems. Let's go to a simpler problem briefly. I kept telling you over and over again, well, we had 10 volts and we had 5 ohms, right? And this voltage was physically connected across the resistor. So the voltage drop across this resistor was the entire source voltage, 10 volts, right? But that's slightly different from what we have here. Here we have 2 resistances. The entire source voltage of 12 volts is kind of connected across both of these guys. So basically the 12 volts is spread across both of these elements, and that's why both of these voltages actually add up to 12 volts. In fact, they must add up to 12 volts. If they don't add up to the source voltage, then you have some kind of like a crazy invention that you could go make lots of money on. It has to. It's conservation of energy. Thinking about the mountain analogy, right? We climb up this mountain to the top, right, energy-wise, okay? And we're at the top, so it represents 12 volts, let's say. Now, we come down a little bit, down the mountain through this guy, and we bleed off a little bit of the energy, right? So we bleed off 4 volts worth down here. But there's still lots and lots of mountain left, so once we get all the way down to the bottom, we bleed off the remaining 8 volts. When we get down to the bottom, there's nothing else left, right? We're at the bottom of the mountain. There's really no more voltage drop that you could possibly do because you're at the bottom of the mountain. Once you get down back around to the source here, you've already used up your 12 volts. It's all been used here, so to speak, to push the current. So there's really, you're back down to where you started with. You're back down to the base of the mountain. That's just an analogy. It's not perfect, but it tries to get the point across that whenever you have these things in series like this, you should expect to see a voltage drop here. You should expect to see another voltage drop here, but the sum of the voltages across everything here should always be 12 volts. If we put 150 resistors in series and we measured the voltage across all of them, they should all add up to 12 volts. Of course, in that case, each little tiny voltage that we measure is going to be real small, right? So that you'll get different values, right? As you can see, this happens here as well. The voltage that you get across the elements is going to depend on the elements that we have here. You can also kind of see that you have 2 ohms here and 1 ohm here. So because this is 2 ohms, most of the voltage drop is going to occur over the 2 ohm resistor. A little bit less of the voltage drop is going to happen over the 1 ohm resistor. So it's kind of like proportionally, this kind of splits up the voltage, so to speak. This circuit's actually something we'll talk a lot more about later. It's called a voltage divider, and it's very practical. If you have a 12 volt source, let's say, and one part of your circuit way over here maybe doesn't need 12 volts. Maybe this part of the circuit over here, maybe it only needs 4 volts. Maybe if you put more than 4 volts on this part of the circuit way over here, it'll blow it up, right? Maybe it's a delicate chip or something like that. So you could, and if all you had was a 12 volt battery, then you could construct a voltage divider like this to basically you would have 4 volts here. You're basically taking the source and forcing it to be split up so that 4 volts lies across this guy, 8 volts lies across this guy. So I could take my delicate circuit over here and build it and wire it up right here to the 2 terminals here. The 4 volts would then be supplying my little delicate circuit. The rest of the energy would be going through over here. So a voltage divider is something very practical if you're building something and you need to control voltage, right? At least from a big picture point of view. It's not something you do every day in really delicate equipment where you're trying to get really precise things, but it certainly works in a pinch if you have a few components laying around and you need to convert voltage. It's a very easy way to do it. All right, that is basically what I wanted to talk about in this section. It's one topic and one topic only, and it's so important that it deserves its own section. We call it Ohm's Law. Basically, it governs what we've talked about in words, that if you have the push, which is the voltage, and your resistance, which is in the way, so to speak, then if you know those 2 values, you can calculate the current flowing in a circuit. Ohm's Law applies to the whole circuit, but it also applies to the individual elements that the power or the electricity is flowing through in a circuit. So basically what we do is we need to look at our elements and say, all right, I is equal to V over R. What's the voltage across this guy? In this case, it was the source voltage. So we put it in there. What is the resistance? We put it in there and we get the current. As we change the value of the resistance or as we change the value of the source voltage, the current flowing in the circuit is going to be different each time. And that's just exactly what we talked about in section 1, qualitatively speaking, there. And then finally, we did this problem, which is very, very telling and very helpful for you later on, because what it's basically trying to show you is that, look, these circuits don't have to be quite so simple. If you just know, if you just know the resistance and the current going through something, you can calculate the voltage across an element. You can calculate the voltage across another element. And very, very important that you can add these 2 voltages up, and that's going to always equal the source voltage. There are a lot of things in here that I could talk a lot more about, but in truth, we're going to get to all of them even in more detail as we go in the next few sections. So stick with me. I promise you that if it's not clear now, it'll definitely be clear as you work more problems. And when I encourage these problems again, make sure you understand the concepts. These circuits are not terribly hard, but what you'll find is that if you blow through this and you don't quite understand what I'm talking about and you just keep going, then what's going to happen is once the complexity gets a little bit out of your bounds a little bit, you're not going to have the foundation to be able to handle it. But just knowing that, hey, there's going to be a voltage drop across here. It's going to be plus minus because the current's going this way. Hey, there's going to be another voltage drop. It's going to be a different voltage drop, but the sum of these 2 voltages has to be equal to the source. That kind of stuff you need to internalize.